In the electronics industry, accurate measurement depends on more than just the test software, the test bench, or the board being tested. Pacta Industry presents an introductory video on the different geometries of test probes. Remember to contact Cotelec engineers for any questions or quotes.
All right, today we're going to dive into a totally hidden world. It's a world that, believe it or not, makes our entire digital life possible, and it all hinges on one single microscopic point of contact.
So just think about it for a sec. What is that secret ingredient? What's the thing that guarantees all the electronics you use every single day are going to work, right out of the box? Now, your first guess is probably the software, right? The code that's running everything. And yeah, that's a huge piece of the puzzle, but it's not the whole story. Not even close. Okay, so what about the hardware? The battery, the computer chips. We're getting warmer, for sure, but that's still not it. So much of the time, the reliability of a billion-dollar production line and, yeah, the quality of that device right there in your hand, it all comes down to one tiny microscopic moment. The instant a test probe actually touches a circuit. To really get what this little component does, you've got to picture it as a kind of bridge. A bridge between two completely different worlds. And this is where it gets crazy. It's this incredible balancing act. See, on one hand, the probe has to be an electrical wizard, right? It's got to create a perfect, clean signal with practically zero resistance. But at the exact same time, it has to be a mechanical powerhouse, surviving the force of millions of contacts, resisting wear and tear, and landing with just mind-boggling precision every single time.
And that's exactly why there's no such thing as a one-size-fits-all test probe. The key to solving this whole electrical/mechanical challenge? It's all about the shape. And that has led to this amazing gallery of super specialized designs. First up, let's talk about the piercers. Think of these conical tips as tiny little ice picks. They're designed to be aggressive, to just slice right through any thin films of gunk or oxidation to guarantee a pure, clean, metal-to-metal connection. Then you've got the grippers. And the most famous one here is the crown tip. So if that conical tip is an ice pick, a crown tip is kind of like a rock climber's hand. It uses a bunch of sharp points to literally grip the surface. That means even if one or two points land on a dirty spot, the others are going to find a clean path for that electrical signal. It's brilliant.
And we're not just talking about 2 or 3 points of contact. Some of these tips have as many as
8 sharp points of contact. That's why people call them self-cleaning. Every single point is another chance to get around any surface dirt and make a perfect connection. It just makes the whole measurement incredibly reliable. Another key player in the gripper family is the serrated tip. This one acts just like a miniature saw. Its sharp edges are fantastic for cutting right across any surface film to make sure you get a really solid connection.
But hang on, what if the surface is super delicate? You can't just go at it with something aggressive. Well, that's when you call in the protectors. A flat tip, it's like a snowshoe. It spreads all that contact force over a much wider area, so it can make contact without leaving a mark or damaging a sensitive part.
And for the ultimate gentle touch, you've got the spherical tip. This is pretty much the most tolerant, most forgiving shape out there. If the machinery is just a little bit misaligned, a sharp tip could totally scratch or gouge the product. A spherical tip, though, it just lands softly, which minimizes pretty much any risk of damage.
So you have this huge toolbox, right? Piercers, grippers, protectors. How in the world does an engineer pick the right one? Well, it's definitely not random. It's actually a super strict, logical process. It really all boils down to answering 3 critical questions. Number 1, what's the target surface actually like? Is it clean? Is it oxidized? Is it delicate? 2, what are the mechanical limits of the system? And number 3, and this is the big one, what is the single biggest risk that could cause this whole test to fail? And the answers to those questions, they point directly to the solution. If your biggest risk is contamination, you grab a gripper. If the risk is damaging something fragile, you choose a protector. And hey, if the challenge is just reaching a really tight spot, you use a skinny little needle tip. The bottom line is this: the shape is always chosen to defeat the most likely reason for failure. Okay, let's zoom back out for a second. We've seen all these shapes, and we've seen the logic behind picking them. But why? Why does this one microscopic decision matter so much in the grand scheme of things? Because choosing the wrong tip, well, it kicks off this absolutely disastrous domino effect. It can cause what are called false failures, where perfectly good products get tossed out, and that can stop a whole production line in its tracks. Or even worse, it can lead to undetected defects, where a bad product gets a passing grade and gets shipped out to a customer. Yeah, this tiny mistake drives up costs, it wears out expensive equipment, and it creates these mysterious problems that are just a nightmare to diagnose.
There's this quote from our source material that just nails it perfectly. The diversity of shapes is not a luxury. It's the answer to a complex industrial reality. In other words, every single one of these unique shapes exists for a reason, to solve a very specific, high-stakes problem. So, the next time you pick up your phone or you start your car, you'll know about one of these tiny, unsung heroes that makes sure it all just works. Which kind of leaves us with one last thought. What other simple objects in your world are hiding a secret, complex reality? Thanks so much for tuning in.